There's something almost ancient about the art of forging steel. The heat, the hammer, the transformation of raw metal into something strong and precise. But what you're about to see at ISAC Company Limited is anything but old-fashioned. This is forging reimagined for the modern age, and it is absolutely breathtaking. ISAC specializes in the forging and mechanical processing of ferrous metals, iron and steel, using an integrated production line that combines traditional metallurgical knowledge with cutting-edge automation. The moment raw steel billets enter their facility, a carefully choreographed process begins. First, the steel is heated in high-temperature induction furnaces, reaching temperatures between 100 degrees Celsius and 250 degrees Celsius. That's well over 2,000 degrees Fahrenheit, folks. At that temperature, steel becomes workable, almost like clay in a blacksmith's hands. But instead of one craftsman with a hammer, ISAC deploys hydraulic forging presses capable of delivering thousands of tons of force with pinpoint precision. The forging stage shapes the metal's internal grain structure, and this is key. Unlike casting or machining from a solid block, forging aligns the metal's crystalline fibers along the stress lines of the part being made. The result? Components that are dramatically stronger, more fatigue-resistant, and longer-lasting. That's why forged parts are trusted in aerospace, automotive, and heavy industry worldwide. After forging, the parts move to the mechanical processing stations, turning lathes, milling machines, and CNC centers, where they're machined down to exact dimensional tolerances, sometimes within a few hundredths of a millimeter. Heat treatment follows, controlled annealing or quenching processes that lock in the desired hardness and toughness. What truly sets ISAC apart is how seamlessly each stage flows into the next, from raw billet to finished, certified component. If you've ever wondered what it takes to restore or manufacture a valve or a pump component that will operate under extreme pressure, thousands of PSI, scorching temperatures, corrosive fluids, then Meccanica Gervasoni is about to open your eyes. This Italian precision engineering company has built its reputation on one promise: surfaces that perform under the harshest conditions known to industry. And the process they use to get there is nothing short of remarkable. It begins with mechanical machining, turning and boring the base component to its rough form on high-precision CNC lathes. Once the geometry is established, the surface engineering begins. Weld overlay, or hard facing, is where things get particularly fascinating. A specialized welding process deposits a carefully selected alloy, often cobalt-based stellite or nickel-based inconel, directly onto the component's working surface. This isn't decorative. That deposited layer is engineered to resist wear, erosion, and corrosion far better than the base metal ever could. Next comes precision grinding to bring that overlaid surface to exact dimensional specs, followed by HVOF, high-velocity oxygen fuel thermal spray coating. In HVOF, powdered carbide or ceramic material is combusted and propelled at supersonic speeds onto the surface, creating a coating of extraordinary density and hardness, often exceeding 70 HRC. It's essentially a suit of armor, applied at the microscopic level. The final step, seats lapping, is where art meets engineering. Using a rotating lapping tool and ultra-fine abrasive compounds, technicians hand-finish the sealing surfaces to achieve flatness measured in microns. A perfectly lapped seat is what separates a valve that holds pressure from one that fails. Every step here tells the same story: precision, patience, and an uncompromising respect for the material. Gears are the unsung heroes of industry. Every conveyor belt, every mill drive, every crane, every wind turbine. Somewhere inside, there are gears turning, transmitting power, keeping the world moving. And for over 130 years, Horsberg & Scott in Cleveland, Ohio, has been making some of the finest gears in the world. Their process begins with massive steel forgings or castings, which are then rough machined on large CNC lathes and horizontal boring mills. From there, the teeth are cut using hobbing machines, a mesmerizing process where a rotating multi-tooth cutter called a hob spirals across the gear blank, cutting each tooth to precise involute geometry. For the highest performance applications, gears go through heat treatment, carburizing or induction hardening to achieve a tough core with a hard, wear-resistant tooth surface. Then comes gear grinding, where diamond-tipped wheels refine the tooth profile to AGMA quality standards, some of the tightest tolerances in mechanical engineering. What makes Horsburgh & Scott legendary isn't just the technology, it's the institutional knowledge, the master machinists who've spent decades understanding how steel behaves. Tradition and innovation, turning together. Bending stainless steel tube without wrinkling it, flattening it, or cracking it. Sounds simple, right? Trust me, it is anything but. And that's exactly why the right machine and the right mandrel setup make all the difference in the world. In this clip, we're watching a 2-1/2 outside diameter stainless steel tube being bent to a 5-inch centerline radius, a relatively tight bend for a tube this size, using the Ercolina Megabender 030 with a full mandrel assembly. The Ercolina 030 Megabender is a hydraulically powered rotary draw bending machine designed for both prototype work and small production runs. It's available with work tables in 5-foot, 10-foot, and 20-foot configurations, making it adaptable for everything from short fittings to long architectural runs. The mandrel, a segmented steel plug inserted inside the tube, is the real hero here. It supports the tube's inner wall during the bend, preventing collapse and ensuring a smooth, round cross-section all the way through. Combined with a wiper die and a pressure die, the system controls every variable simultaneously. Watching the machine work, you realize this is controlled, deliberate precision, stainless yielding to geometry, 1 degree at a time. There are fast machines, and then there are machines that make you rethink what fast even means. The Heller HF 5500 with the DC100i spindle belongs firmly in the second category. Heller, a German manufacturer with decades of pedigree in high-performance machining centers, engineered the HF 5500 specifically for 5-sided and complex workpiece machining, the kind of demanding multi-surface jobs that used to require multiple machine setups and far more time. The headline spec? Performance up to 5 times faster than conventional turning centers. At the heart of that performance is the DC100i spindle, a direct-coupled, high-torque motor spindle capable of delivering exceptional cutting force at both low and high RPM ranges. This isn't just about spinning faster, it's about maintaining cutting power and surface quality under the full load of heavy steel removal. The machine's twin pallet system allows one workpiece to be machined while the next is being loaded, slashing non-cutting time dramatically. Thermal compensation systems continuously monitor and correct for heat-induced dimensional drift, keeping tolerances razor-tight across long production runs. What you see on screen is a cascade of chips flying as hardened steel yields to carbide tooling at speeds that honestly feel almost cinematic. This is what modern German engineering looks like in full flight: efficient, powerful, and relentlessly precise. Here's a question worth thinking about. How many bearings do you think are turning right now, in this very moment, inside the machines, vehicles, and appliances that surround you? The answer is almost certainly in the thousands. Bearings are everywhere, and almost no one thinks about them until one fails. That invisible, critical work begins right here on the bearing assembly line. The process starts with component preparation. The inner race, outer race, and rolling elements, whether balls or tapered rollers, arrive from precision grinding operations, where their surfaces have been finished to tolerances measured in micrometers, a fraction of the width of a human hair. Before assembly, each component is ultrasonically cleaned, removing every trace of machining fluid and particulate that could compromise bearing life. The automated assembly machines then take over. In a ball bearing assembly cell, a sophisticated pick-and-place system positions the inner race inside the outer race, and an eccentric loading mechanism, sometimes called the snap-fill process, inserts the maximum possible number of balls into the raceway. A cage, typically made from stamped steel or machined brass, is then inserted to keep the balls evenly spaced, reducing friction and preventing ball-to-ball contact. For tapered roller bearings, the workhorses of wheel hubs and gearboxes, rollers and cages are assembled with even tighter positional control, since the geometry of the taper is critical to how load is distributed across the rolling surface. Greasing and sealing follow, the right grade and quantity of grease injected precisely, then rubber or metal shields pressed in to protect against contamination. Every completed bearing then passes through noise and vibration testing spun at speed by the test rig while sensors listen for the faintest irregularity.